All right, let's get going with our second session. Tangents and normal application of derivatives is the chapter that we are talking about. And in this session, we are going to take some miscellaneous questions, questions where you're not asked to find tangent to the given function at a given point, but there is something more that you need to look out for. So here we go. Let's start with our slides and get you going. So let's see, we have our recap as well to begin with, so that those who were not around last time or had not seen the recording are ready to take off with this work that we have here. So we are looking at the second session on tangents and normal. Now what we are looking for is just first to recall what the tangents and normals are and how we had figured out to what given a curve. So if I have y equal to f of x, how do I find the equation of the tangent to this curve and also the normal? So if we have an understanding that derivative of a function is nothing but the slope of the tangent to the given curve at any point, then in case I am asked or am interested in finding the slope of the tangent to the curve at the point x1 comma y1, then it's nothing but the value of the derivative at this point. And that is what is needed to form the equation of the line, which is our tangent line. Because we have the 1-point slope form of the line y minus y1 is equal to m times x minus x1. So m is the slope, which in this case is dy by dx at x1 comma y1. Once we talked about the equation of tangent to this curve, we also were in a position to talk about equation of normal to the curve at a given point. Normal is a line which is perpendicular to the tangent at the point of contact. And therefore, the slope of normal will be the negative reciprocal of the slope of the tangent. And therefore, you are looking at negative 1 over dy by dx at x1 comma y1 to be the slope of normal. And so we are ready to form the equation of the normal to the given curve y equal to f of x at the point x1 comma y1. So we need basically two things, slope and point, to form the equation of normal or tangent to the curve at a given point. So let's see what our next question says. We have a problem which says, find the equation of the tangent to the curve y equal to x minus 7 over x minus 2 times x minus 3 at the point where it cuts the x-axis. So I need to form the equation of the tangent to this curve at a point, and that point is being described as the point where it cuts the x-axis. So where do you think this function is going to cut the x-axis? Think about it. What does it mean by a point on the x-axis? Simply that y coordinate must be 0. And that is where we begin. So put y as 0 and you have your point. X is 7 and y is 0. So what else we need therefore in this case is the slope of the tangent. And for that we of course need to find the derivative. So differentiating with respect to x, we have our a little bit of work because you have quotient rule to use, and some simplification will lead to a very simple calculation, and you have dy by dx at x is equal to 7 to be same as 1 over 20. And therefore, we are ready to form the equation of the tangent line. So we have the equation of the tangent line to at the point 7, 0 as y minus 0 is equal to 1 over 20 times x minus 7. As I said in the last session also, you must make an effort to rewrite the equation in the general form. So it must have a look of ax plus by plus c equal to 0. So rearrange and write your final answer as x minus 20y minus 7 equal to 0. Now again, this was a simple question, wasn't it? So let's take a look at our next question. This one is again in your NCRT textbook. So in case you have not been able to note down the question, you can always refer back to it. And of course, the slides will be shared again through Edmodo. You can watch the recording. At the same time, you can go through the slides independently in Edmodo. Let's take our next question. Great. Now we are looking at some difference in this question. Here the question is, find the equation of the tangent to the curve given by x is equal to a sine cube t, y is equal to b cos cube t. So what are we looking at here? The function is something special. Remember, these are the parametric functions. And therefore, at a point where t equal to pi by 2 makes complete sense. As t varies, x and y values vary and they define the function. So this is a stage where you will start thinking about, right, we did learn how to find the derivative of parametric functions. So that's definitely going to come in hand. So we are looking at x and y given point where the tangent is to be described is when t is pi by 2. So when you put t as pi by 2, you get x as a and y as 0. And therefore, we are ready to start off with finding the slope because we already have the point. Slope, yes, you do need dy by dx. And parametric differentiation requires that you find the derivative of x with respect to t and find dy by dt. Dy by dx is the quotient of derivative of y with respect to t divided by derivative of x with respect to t. In this case, very simply, it simplifies to negative a by b cot t. And therefore, the slope of the tangent to the curve at t equal to pi by 2 will be nothing but the value of the derivative at t equal to pi by 2, which, well, we are happy to have it all turn to 0. And therefore, the equation of the tangent at the point that we are interested in, which is at t equal to pi by 2 and x was a, y was 0, turns out to be y minus 0 is equal to 0 times x minus a. And hence, in this case, the equation of tangent is simply y is equal to 0. That is the x-axis. So even if the function is in the parametric form, you are good to go as long as you remember how to find the derivative of parametric functions. Let's see what we have next. Our next question says, for the curve y is equal to 4x cubed minus 2x to the power 5, find all the points at which the tangent passes through the origin. Now, this is an interesting question and interesting function, in fact. So take a look at the complete situation here. Find all points on this curve at which the tangent passes through the origin. So what's striking you immediately as you look at this equation? What kind of a function do you visualize happening here? Do you see something special and do you connect it with the origin as it stands? Definitely, yes. Origin is a point of the curve. So the curve is passing through the origin. And we are talking about finding all, therefore, other points at which the tangent passes through origin. So there are more points at which the tangent passes through origin. So, of course, later in this chapter, we will learn how to do a rough sketch of such a function. But I just love to use various other tools right now, and you can as well, to actually visualize what kind of a function are we talking about. We have never used a fifth degree function. So what kind of a curve does it actually look like? Because it does pass through origin. And then we are talking about tangents maybe at multiple other points at which are such that they pass through origin. So if you use any other tool like GeoGebra or Desmos to plot this function, you will realize that this is what the curve looks like. Isn't it interesting? And therefore, when we talk about tangents at points which passes through origin, then you see here that this is something special happening. We are going to end up with, other than the origin, we are going to end up with two more points at which the tangent passes through the origin. So let's see how we get these points. Now, in this case, since we don't know the point, we assume that to be x1 comma y1. Remember, that's what we did in our earlier set of questions as well. And then we start with a discussion about what would be the slope of tangent. Do we have a condition by which we can relate the givens so that we can find out the unknowns? So in this case, you have assumed the slope, the point at which the tangent is drawn to be x1 comma y1, but we also know that this tangent is going to pass through origin. So in fact, the line is passing through the origin, and there is something special that you must relate when you think about line passing through the origin. So what we do remember is that any line that passes through origin has the equation of the form y is equal to m times x. And that is going to come in handy to say that therefore the slope of this line is going to be always same as y1 over x1. You can also use the 2-point form. You have one point which is the origin and the other point is x1 comma y1. So the slope of the tangent line using the join of the 2 points is nothing but y1 minus 0 upon x1 minus 0. So we do have the slope as y1 over x1. At the same time, do we know how to find the slope of the tangent to a curve at a given point? I think every one of you must be able to, because that's what we are learning in this chapter. So if you find derivative of y with respect to x and find the slope at that point, so if I find dy by dx, that's nothing but 12x squared minus 10x to the power 4. So the slope must also be 12x1 square minus 10x1 to the power 4. This must be equal to y1 over x1. But again, y1 is nothing but the value of the function when x is equal to x1. Because x1 comma y1 is a point on the curve. Never ever forget that, because that's the most essential information that's known to us. And therefore, when you equate these two conditions, you have a condition in x1. And let's just try to solve. Also remember that here, when I took the slope to be y1 over x1, I'm taking y1 and x1 values to be other than 0. So I'm assuming that yes, the curve does pass through origin. We saw it as well. And when I assume these values of the point at which the condition is satisfied, we are taking that x1, y1 to be a point other than the origin. And therefore, there is no worry about x1 coming into the denominator. And therefore, if you cancel x1, that's also perfectly fine. And that is what you need when you start off simplifying this condition. So as you simplify this condition, you would get x1 to be, yes, one value, 0, which we have considered earlier. And the other two values are 1 and negative 1. And with that, if you substitute it in the expression y is equal to 4x cubed minus 2x to the power 5, you get the 3 points that we saw earlier as well in the graph. So you have the required points as 0, 0, 1, 2, and negative 1, negative 2. I hope the question has made sense to each one of you. And in case you still have doubts, please do let me know. Let's consider another question. This is also in your NCERT textbook. There's just one of such questions, but interesting to note and think about a possibility of curves cutting at right angles. What would one mean by angle between two curves, first of all? Curves are at right angles if 8k square is equal to 1. But when we think about angle between two functions, we have normally and in general thought about them as lines. Angle between two intersecting lines, perhaps. Angle between two curves is a concept that actually reduces down to angle between the tangents to the curves. So here, if I have two intersecting curves, the point at which they intersect is the point at which we are figuring out the angle. So we are going to be interested in finding, actually speaking, is the requirement would be of the problem, the angle between the tangents to these two curves at the point of intersection of these two curves. So first and foremost is, do we know where these two curves intersect? And if you don't know, or which is not given directly, one would solve for it. So how do you find the point or points of intersection of two curves? Points of intersection are nothing but common solutions. So if we start solving these two equations simultaneously, I can take the value of x as y square, substitute it in the xy equal to k, and I have y as the cube root of k. Therefore, x would be, well, 2/3 root of k. So the point of intersection is, let's call it A, is k to the power 2 by 3, comma, k to the power 1 by 3. So this is the point at which, if I know the equation of the tangent to the first curve and the tangent at the second curve, then we are good to go and find this angle. At the same time, do I really need to form the equations of the tangents? Or to find the angle between two lines, if we know the slope of the two lines, would that be adequate? Surely. You're looking at and understanding that angle between two lines, if it is denoted by theta, then theta is the tan inverse of m1 minus m2 divided by 1 plus m1 m2. Coordinate geometry of class 11 coming in use. And that is what we will think about now. So we'll first find the tangent, slope of the tangent to the first curve at the point of intersection, and therefore we differentiate x equal to y square, get dy by dx, and then the slope at A is, let's denote it with m1, is the value of this derivative at the point A. And in this case, it takes the value 1 over 2 times of k to the power 1 by 3. I'm sure you can find and you will find the slope of the tangent to the second curve at this point. So I have x times y equal to k. So if you differentiate the second curve with respect to x and then find the slope of tangent at A, you have the value m2. So x times y equal to k, when I differentiate with respect to x using the product rule, it's x dy by dx plus y equal to 0. dy by dx is negative y over x. And therefore slope, that is m2, is the value at A, and therefore it will be negative k to the power 1 by 3 divided by k to the power 2 by 3. So we have m1 and m2. We know that they will cut at right angles, the curves will cut at right angles if the product of the slopes is negative 1. So if I take m1 times m2 and put it equal to minus 1, I'll get a condition in k, and hopefully that would be the required condition. So let's see what happens if I have m1 times m2. In this case, it is nothing but 1 over 2 times k to the power 1 by 3 minus into minus k to the power 1 by 3 divided by k to the power 1 by 2 by 3. Well, you can see that k to the power 1 by 3 would get cancelled, negative would get cancelled, and you'll have something like 2 times k to the power 2 by 3 is equal to 1. Well, you can cube both the sides and you have your required condition. So the two curves will cut at right angle if 8k square is equal to 1. So if the question asks only to find the angle between the two intersecting curves, you also can go through the same procedure, find the point of intersection, and then find the slopes of the tangents to the two given curves at the point of intersection and use the formula for angle between two lines to get the angle between the two curves. In this case, it was the requirement just to get a condition in terms of k, which we have achieved. All right, let's see what we have next. Great, another miscellaneous style of question, which kinds of rounds up the topic with something different. At least it sounds different when you read it for the first time. So here it says, show that the normal at any point t to the curve x is equal to a cos t plus at sin t and y is equal to a sin t minus at cos t is at a constant distance from the origin. So we are talking about normal at any point t. So of course it's a parametric function at any point t. Now that is the difference. We did do one question on parametric functions just a while back, and there t was taking a specific value pi by 2. Here it's at any point. So they're saying that the normal to this curve at any point is at a constant distance from origin. So the distance of the normal to this curve at any point when measured from origin is a constant. It does not depend on t. Now that is what is special about this question. So we are not interested in finding equation of normal at a specific point, but equation of normal at any point. And once we have that, then distance from origin, do you think you can calculate? Given equation of a line in the form ax plus by plus c equal to 0, did we ever learn something which shows you how to find distance of the point from the origin? I'm pretty sure you will recall soon enough. So let's get started first. To find the equation of normal, I need the slope of the normal at any point t. And therefore, you need dy by dx. So let's find the derivative with respect to x. And in this case, you'll be very surprised that dy by dx turns out to be just tan t. Now I'm going to leave this as a question mark for you. Figure it out for yourself. How did we get dy by dx to be tan of t? I'll give you a minute if you're around to work it out as well. Take a look and see if you have been able to figure out what and how we get that derivative. So dy by dx, parametric differentiation, gives you dy by dt divided by dx by dt. Let's see if you can figure it out quickly. I think you will be. Remember how to be careful where you have a product, you use with the product rule, and you will find that lots of terms get simplified. dx, then the slope of the normal is going to be nothing but the negative reciprocal of this quantity. And in this case, it's at any point t. So I just have to take negative 1 over dy by dx. And so the slope at any point t turns out to be negative cot t. So the equation of normal at any point t starts looking like y minus y1. Now y1 is going to be nothing but the point at any t. So this is going to be the entire a sine t minus at cos t. X minus x1, you have your entire expression as it is. I have chosen to write cot t as cos t over sine t, because you will soon realize that you need to simplify this. Like in all other previous questions, you must try to rewrite this equation. And having cot t there would not help. As soon as you write negative cos t over sine t, I'm sure you will be tempted to do some simplification, cross multiply, simplify, and see that lots of terms gets cancelled. If you observe this expression here, I have y sine t, then I have negative a sine square t minus at sine t cos t. And on the other side, I have a cos square t, and then I also have at cos t sine t. When I open the brackets, take care of the negatives, at sine t term gets, sine t cos t term gets cancelled on both the sides. What happens to a sine square t and a cos square t? Right, a cos square t plus a sine square t is nothing but a. So you get the linear, not the linear, but we are looking at the equation as, yes, the linear equation in x and y to be x cos t plus y sine t equal to a. That's the normal to the curve at any point t. So if as in the previous example, if t was given to be say pi by 2, we can substitute t as pi by 2 and I'll have equation of the normal to the curve at t equal to pi by 2. Right now, we are interested in something better. We are interested in finding the distance of such a normal from origin. So how do I find the distance of a point from a given line? This is what we had used and learned in class 11. Distance of point x1 comma y1 from the line ax plus by plus c equal to 0 is nothing but the absolute value of ax1 plus by1 plus c divided by root of a square plus b square. So you replace x and y by the point from which the distance is being calculated, and you are looking at dividing by root a square plus b square. Now this is the formula which is definitely needed here. And therefore, distance of normal from origin, when you replace x cos t plus y sine t equal to a, so I bring a on the left side and I have 0 times cos t plus 0 times sine t minus a divided by root of cos square t plus sine square t, which, well, is nothing but a and is a constant. And therefore, we are ready to conclude that normal drawn to the given curve at any point t is always at a constant distance from origin. So if you look back at what we had done in our discussion, we have not done anything too different, but we are not talking about the normal at a specific point. And that is what baffles some of us. You would possibly start looking for where is that point at which I have to find the equation of the tangent or normal. So it is at any point t, so you're good to go with your dy by dx as you simplify to be the slope of the tangent to the curve at any point. And that is the start of the question, which would take you very swiftly to the conclusion. So I think we are good to go as far as this particular topic is concerned. And I'm going to leave you, and I trust that you will find time and you will be hopefully motivated to catch up with the rest of the exercise. If you still have a problem, please do post it on Edmodo, and I will make an effort to reach out and to give you the solution in one way or other. In our next episode of Hangout on Air, in an effort to pack in a little in this month of June, we will move on to our next topic. So we are going to be talking about increasing and decreasing functions. So I hope more of you will join me there. And those who have not joined me today, I hope you will find time to go through the recording and do the needful. So let's say goodbye to you right now and hope to see you soon. Bye.